Dr. Jonathan Clarke. And Jonathan has worked in the mining industry for, looks like over 20 years, even longer. But he comes to us from the Mars Society, so he's been all the way through his work around the world in mining. You've actually been a closet Mars miner, Jonathan.
Indeed.
And you're going to talk to us about what it will take to mine on Mars. Is that right?
Something along those lines.
Good stuff.
Okay, from floating around asteroids, let's get our boots onto the ground, literally as well as metaphorically. Why Mars? I mean, why are people like me interested, and many other people interested in going to Mars? Well, there are many reasons. I've listed them there. Your mileage of these may vary, but it's accessible. Not as accessible as some asteroids, but 20 kilometers a second to Mars of atmospheric braking compared to 16 kilometers a second for the Moon. The surface can be readily explored with vehicles and with people wearing EVA suits. It's scientifically interesting. The place has considerable potential for past and present life, and if there isn't any, then the question is why there isn't any is also very important. There's a detailed atmospheric history for climatologists, and there is a complex geology, including preservation of the first billion years of planetary history. And there's also long-term potential for human settlement. There's substantial gravity, which you may need as biological organisms. There is some useful radiation protection from the atmosphere, and of course you can bump that up with regolith. It's got Earth-like seasons and a day. And there are abundant and diverse potential resources, which is what I'll be talking about today. And NASA is taking Martian resources seriously. There's been reference to this conference already last week at the workshop at Houston, first landing site exploration zone workshop for human missions to the surface of Mars. And there's people in this audience, hi Andrew, who are there. And part of the criteria to select these areas, and something like 50 areas were selected, included resource zones of interest. And in a parallel report, the roadmap for the next steps of the journey to Mars, the word commercial was mentioned 50 times, not specifically in connection with Mars, but certainly with a pathway of going to Mars. And this is a landing site that I, along with colleagues from NASA Ames, put up there, Meridiani Planum, which is the site where the Opportunity rover has been trundling around for the past 11 years, and where, all being well, the European Scarpelli lander will touch down sometime next year. And there's a large number of regions of interest here with potential for ice, for polyhydrated sulfates, there's also a water resource, for clays, for regolith materials, which in fact occur everywhere. And they're also around the crater rims, because impact craters generate large, long-lived hydrothermal systems. There's potential for hydrothermal vein deposits, and we've seen this around some of the craters. Endeavour crater there, up at 6 here, where there is elevated zinc in veins in altered rocks along the crater rim. Why do we want to use Martian resources? Well, each person on Mars for a 600-day mission requires about 1.5 tons of water, and that's with 90% water recycling, assuming about 25 litres of water per person per day. Just over half tons of oxygen. And then for the return journey, you need propellant. I mean, if you assume methane and oxygen, there's something like 25 tons of these propellants to come back directly to Earth, or if you just want to go into Mars orbit, about 3.5 tons of propellant per person. So for a 4-person crew on Mars, that's about 8 tons of water and breathing gas, or about 100 tons of propellant for direct return, or 14 tons to low Mars orbit. Or if you prefer 6-person crews, it goes up by about 50%. Now there's about a 1 to 5 gear ratio for mass on the surface of Mars as opposed to mass in low Earth orbit. So using Mars resources could save the amount of mass we need to put onto the surface of Mars by up to 800 tons. So that is a very substantial reason to use Martian resources to minimize the mass that we need to land there, particularly where the masses are most critical, which is propellant, drinking water, and breathing gases. In other words, ISRU for crewed expeditions. Lots of grandiose plans for Martian settlements, for terraforming, all that sort of thing, but unless we actually have boots on the ground, none of that will happen. So we're looking at raw materials, water, compressed gases, propellants, oxygen, carbon monoxide, methane, hydrogen, drinking water, the breathing gases, nitrogen, and also argon. There is almost as much argon in the Martian atmosphere as there is nitrogen, and we can use that as a buffer gas as well. And of course energy, primarily solar, that we can access. So working through these, and again the focus is mainly on expeditions, potential Martian resources start with the volatiles. And we have three examples here in the wonderfully named Louth crater. In the northern hemisphere of Mars, there's a large deposit of ice. This is the southernmost deposit of exposed ice on the Martian surface. And you also have this very beautiful seasonal frost condensing out of the atmosphere on the south-facing rim. But the Mars atmosphere is itself a resource, 95% carbon dioxide, 4% nitrogen, 2% argon. And because we know the composition of the Martian atmosphere is actually the easiest resource that we can access. And it's also everywhere. Most Mars mission studies of the past 20 years have used a split mission architecture. Essentially, you send the stuff that's not wanted for the crew on voyage to Mars ahead of time. This includes making propellant for your return journey, and your crew goes there 18 months later, about 500 days on Mars later, when everything is ready for the journey. And this window, this 26-month, 500-odd day window, is an opportunity potentially for commercial providers. So if you need so many tons of water, so many tons of propellant, so many tons of oxygen, nitrogen and so on the surface of Mars, potentially an organisation such as NASA, European Space Agency, some Mars consortium could contract out the provision of those supplies ahead of time to have them waiting there when the crew arrived. And here's a rather nice fanciful diagram of an automated ISRU plant doing all sorts of things, getting ready for the crew to arrive and use. Okay, so focusing on water. How much water would we need to use or to collect on Mars to supply our needs? And so I focused on three Mars mission studies, the classic Mars Direct study, the one that Mars Society Australia involved, the Mars Oz study, and the NASA Design Reference Mission version 3. Each of these studies imported hydrogen, 6 tons, 1.6 tons, 5.5 tons, and this is the water equivalent of that hydrogen. So if you end up processing that from Martian resources, you basically would need to provide between 25 and 100 kilograms of water per Martian day per soul, which is not a lot of water. I mean, 27 kilograms of water is something you would pick up in 2 buckets. 100 litres, well, that's about 5 or 6 buckets. So not a lot of water. So if you can extract that, you can start transforming Martian logistics. And here's a case study from Meridiani Planum, where I've had a long-standing interest, where the Opportunity rover has trundled over 40 kilometres, and where there are large quantities of polyhydrated magnesium sulphate minerals. There's small amounts of epsomite, which everybody knows, Epsom salts, which is 50% water. There's kieserite, which is 40% water. And there's all these other ones, hexahydrite, 47% water. There's this marvellous thing called Meridianiite, which has been synthesized in the laboratory and is hypothesized to exist on the surface, which is over 60% water. And about 20 to 30% of the rocks or the Burns Formation that make up Meridiani Planum consists of these minerals. So 10 to 20% H2O, and these minerals mostly dehydrate between 135 and 350 degrees. From a planetary protection point of view, it's important because it's not biologically available. It's locked up, as Leslie spoke, as a hydrated mineral. It's not water that bugs can access, and so you can mine the stuff without worrying about releasing exotic life forms or perhaps destroying some Martian habitat. And here's a graph of the dehydration temperatures. So I mean, some things start dehydrating at very low temperatures, but this window of about 100 to 350 degrees is where a substantial amount of dehydration occurs. The problem is we don't actually know how much energy that takes. This is something that needs to be investigated. What is the desired efficiency? Work further down the track. So I've done some numbers here on if you have 20% recovered water, you need to excavate 270 tonnes to supply 54 tonnes of water for a full earth return, which is half a tonne of water a day, which comes down to about quarter of a cubic metre at a density of 2, which is probably about right. That's not a lot of dirt to mine for a fairly heavy requirement. So if you do some of these other missions which require less water, you're starting to talk about 130 kilograms. You could do that with a shovel and pick, as certain people describe mining as requiring earlier today. You wouldn't do that, but it is something that you would shift in an afternoon in the garden. Talking about Meridiani, there are other potential resources there. The waste from water extraction for polyhydrated sulfates consists of magnesium sulfate, which is an electrolyzable salt. All magnesium on Earth is produced by molten salt electrolysis from magnesium chloride, but potentially we could research magnesium sulfate extraction. These sand dunes, these dark sand dunes that cover the surface, are mixed hematite and basalt sand. We can extract the hematite, five minutes, thank you. We'd extract the hematite from there by a cyclone separator and potentially process it to extract the iron, perhaps by iron carbonyl processing. They also contain 55% basalt, and as we have heard already today and from the last conference, basalt is an extraordinarily useful material. We can use it, we can cast it, we can extrude it, it can be spun into fabrics, it can be sintered with 3D printing into basic structural materials, which can be used to make tiles. It's a very useful material and it's pretty well everywhere. Not entirely everywhere, but anywhere between 50 and 100% of the area of Meridiani Planum contains this basalt, completely unconsolidated. And of course the sand itself is useful material. You can bag that and use that to construct, or pile it up to construct berms or bury equipment that you want to protect from radiation. So in conclusion, resource identification is a high priority for crewed missions to Mars. Mars has a diversity of potential resources, including volatiles for propellants, water and breathing gases, hydrated minerals, water extraction, regolith for low-grade construction work, including gypsum, which I haven't talked about and is a very useful material, locally available basic metals, hematite, magnesium, and many of these technologies are readily testable on Earth, unlike asteroid mining, because of the similar gravity, the similar materials. And one thing I'll also point out is that there are many analogue materials we can use. At Cooper Pedy, famous opal mining town in Australia, just outside that, there's the world's largest epsomite deposit, hydrated magnesium sulfate, within a couple of meters of the surface that you can go out and dig and test these processes. And there are potential commercial opportunities, again, as people have been saying, not for export to Earth, but for sale and use on site to potential users. Questions?
So Jonathan's Australia is a very good place to actually test and develop some of these technologies.
There are many places in the world to test, and you need to select the best ones for what you want to do. UNSW have generated a lot of basalt, crushed basalt as a lunar simulant. That is also a good simulant for some of these basalt sand dunes on Mars. We certainly have lots of hematite in Australia, which we can use to simulate hematite extraction from blueberries, and pelletizing plants actually produce reasonable analogues or facsimiles of those hematite blueberries. And we have large amounts of gypsum and epsomite out on dry lake beds and in weathered regolith to test other processes.
Cool, terrific. Questions? Yes, ma'am.
If we referred very briefly when you were talking about Burns Cliff to the fact that if you mined the sulphates there, they weren't, microbiologically, remediated or anything. But you haven't really referred to planetary protection issues anywhere else. I mean, that surely must be a concern.
Yes, there are many planetary protection issues that have to be addressed if we're going to go to Mars. I guess my assumption in this presentation is they have been addressed, and we can do these things in a way that keeps them within acceptable limits. I simply mentioned the planetary protection issues of epsomite or magnesium sulphates, is that extracting the water from that raises fewer issues than, say, quarrying ice that may well have, or potentially would have, dormant microorganisms.
I mean, it does strike me that we almost need another X Prize to demonstrate some kind of mine resources and create enough closed circuit oxygen, water, someone for a 4 to 6 person crew. We almost need to demonstrate that as an exercise, don't we?
Yes, and one of the nice things about mining something like epsomite or gypsum to extract water is you can do it full scale. I mean, 100 kilos a day is something that you don't need to do a pilot plant. You actually can do the full-size plant, at least here on Earth. You might want to send a smaller one to Mars, but you can actually do it full scale here on Earth and without worrying about what happens when you scale it up.
I guess repeating that every day to generate the entire amount that you might need for your vehicle or for the life support system, repeating and doing it with robots and no people allowed, that would be a really interesting challenge, I guess.
So it's got to be a very simple task. So you don't want to be doing something that's trying to follow a vein of ice in a rock that goes in every direction. You want something that just, this epsomite layer or this sulphate layer goes in every direction for 50 kilometers and there's hundreds of meters thick, and we just scoop up the top. Or this basalt sand dunes, we just have to sweep it up with something like a street sweeper, and then run that through a cyclone and dump the stuff that's not hematite and keep the hematite and keep the basalt, as the case may be.
We should get Dyson involved in this project, I think. And that would be a great one, because they've got that whole thing going.
Yeah.
Thank you very much, Jonathan.
No worries.
We're going to have a quick bathroom break and then get right back into it. So we've got a few minutes. Thank you.